So we're going to continue reviewing here from the summer, and we're going to go through moles, molar masses. We're going to figure out how do they get the average atomic mass units from the periodic table. That's mass spectroscopy. And then lastly, percent composition and empirical formula. So let's get started here. So these are things that you definitely went over last year in first year chem. A lot of people use N for moles. A lot of people use M for mass. A lot of people use MM for molar mass. You don't have to use any of those abbreviations, but that's typical. And what else do we know about the mole? So the mole is kind of like a dozen. It can a dozen. You can have a dozen eggs, a dozen donuts, a dozen of anything, and it's just a unit. The mole is just a unit, and it means 6.02 times 10 to the 23rd of whatever you're dealing with: molecules, ions, atoms, whatever. And then we also have the periodic table, and those masses on the periodic table would be how many grams are in 1 mole of that item. And then if you have a gas and you are at standard temperature and pressure, then 22.4 liters of any gas equals 1 mole. So we could use any of those for conversions. So you might get a question that could look something like this. So if you have different combination materials like carbon, water, and carbon monoxide and helium, could you rank them and rank them in terms of different ways? In this case, increasing mass. So I'm going to write a couple things up on the board here. And so if you have 1 mole of carbon, you have 12 grams of carbon. Now it's actually 12.01, but we can round it to 12 for this purpose because we're just looking to rank these. We're not looking for specific answers. 3.01 times 10 to the 23rd turns out to be half of a mole, because a mole is 6.02 times 10 to the 23rd. So water is H2O. And if I go on the periodic table and find 2 hydrogens and 1 oxygen, that would equal 1 gram plus 1 gram plus 16 grams. And now, again, I'm rounding to the nearest whole number. But if this was a question where you needed to write down numbers for answers, I would go with the periodic table. So anyhow, that's 18 grams for a mole of water. But since you only have a half a mole of water, you have 9 grams of water. Okay, and then we already have the carbon monoxide. It says it's 7 grams. And then 44.8 liters. Now, it doesn't mention this. I'm just going to throw this in there, that we're going to say that it's standard temperature and pressure. So at standard temperature and pressure, 22.4 liters equals a mole. So if you have 44.8, that's 2 moles. And how much does helium weigh on the periodic table? It's 4 grams. So if you have 2 moles, that would be 8 grams. You might be able to do all that in your head. I'll show you how I did that in a factor label style. But if you can do it in your head, that would be fine. So 22.4 liters equals 1 mole of any material. And then a mole of helium weighs 4 grams. So 22.48 divided by 22.4 is 2. 2 times 4 is 8 grams. And I'm just using decimal places, but I could have just said whole numbers there. Okay, so it looks like we got 12 grams, we got 9 grams, we got 7 grams, we got 8 grams. So you could rank those in terms of least to most, and I think we already gave you, and this will happen often, I'll give you the answers already. We just have to figure out how do we get to those answers. Let's double check that those answers are right. Carbon monoxide is the least, then we have helium next, then water, and then carbon. Yeah. Okay, so let's give this one a shot down here. The same scenario, materials we have, but this time increasing particles. So what kind of particles? We'd have to convert everything from moles to particles. So we had what, 1 mole of carbon. So for carbon, that is 6.02 times 10 to the 23rd. What else we got? Water. We had, actually those particles were already given to us. We didn't even have to do anything with that one. It's not letting me write down water in that spot right there. I might be getting a little bit low on here. But that is 3.01 times 10 to the 23rd. And then what else we got? We got the carbon monoxide, and it said we had 7 grams of it. You know what, maybe I'll do the factor label for that one over here. 7 grams of carbon monoxide. And then on the periodic table, we have 1 carbon, that's 12, and oxygen, that is 16. So that is 28 grams in 1 mole. And then 1 mole is 6.02 times 10 to the 23rd. So it looks like that's a quarter. 7 divided by 28 is a quarter. And then we'll have to multiply that by 6.02 times 10 to the 23rd. And I got, we'll write that right here, 1.5. There's some numbers after that, but again, we're just ranking these. So 1.5 times 10 to the 23rd. So we don't need all those digits for this. And then the last, we had 44.8 liters of helium, which we had already figured out that was 2 moles. So 2 moles is 2 times 6.02. So you could write it a couple different ways, but I'll do this to make it look all to the 10 to the 23rd. So I think the helium is definitely the largest. And then 6.02 is more than the other numbers. So that's why carbon was the second biggest. Water was 3.01. And then 1.5 was the least. So you have to be kind of able to do those factor labels either in your head or on a piece of paper pretty quick. Okay, let me move this arrow over a little bit. Okay, so next is, you don't have to know a lot of details about this, but someone might ask, well, how do you get those average atomic mass units on the periodic table? So for instance, carbon doesn't say 12, it says 12.01. That's the average of all the isotopes of carbon, their relative abundances and their masses, and they average all those together, and that's where those numbers come from. Well, where do they get those average abundances and those masses? They get it from a machine, pretty expensive, pretty difficult machine to use, called a mass spec. Well, a lot of people round it to mass spec. And so you can put a sample in there and you can figure out different isotopes of in this case, carbon or nitrogen or whatever you wanted to do. So you guys didn't learn that maybe last year, but you learned how to do the math. And the math is percent abundance times whatever mass of that isotope. And then you can add it to any other isotopes that you have. In this case, I only showed 2, but maybe for some elements you might have a whole bunch. So it looks like you could do this in data form. You could also do in graph form. This is a graph. So 80.1, so this would be 80.1% means 80.1 divided by 100. and its mass was 10. And then we had another percent abundance. And again, percent abundance means divided by 100, and its mass was, so let me put a multiplication in there, and that was 11. So if you did that math, I think it would come out to be very close to that number. And then you could then also figure out what element on the periodic table this is. You probably didn't even have to do all that math to do this, but 10.199, if I look on my handy dandy periodic table, doesn't come out to be any of these. I must be missing, there must be a little bit probably of another isotope here, and that would change these, but I think it's going to end up being boron, but boron has a molar mass of that number. So that's what I'm saying. There's probably more isotopes, but I took this from your textbook, and they try to give you an easier problem with just 2 isotopes. But the math is perfect with the data that was given to us. But the next one, I think we're going to have to try to figure out what element it is on the periodic table. So let's give that one a shot. So this one, you're going to be hard pressed to do math with this because it doesn't give you the actual percent abundances. It just gives you an idea. I would say that first line is pretty close to 50, but I can't guarantee that's exactly at 50 there. But we do know that most of the isotope mass has most of the isotopes have a mass of 90. Half of them, approximately half of them. So it's definitely going to have to be greater than 90, but it's not going to be a lot more than 90 because these other isotopes are not in a big abundance. Yes, they have more mass, but they're not really that abundant. So what could it not be? Can't be that mass. 88.91, that would be down here, in this range, below any of the isotopes. It's got to be between that, and it's going to be closer to that side than it would be in the middle because we have so much of the 90. That doesn't make any sense. It can't be 238. We're not even anywhere in that ballpark. So now we're down to these two, and you could try to do all the math. And so the math would be, we have a mass of 90, and we have a close to a percent abundance of 50%, and then you'd have to add up all the other ones. And what do we have? We have 1, 2, 3, 4 more to do. So, whoops. So you'd have more to do there. I don't think you'd really want to do all that math, but I would bet that if you did all that math, it's going to be a shade over 90. And so I think that's going to put us into answer B. Okay? And you're going to have some questions when we get to tests and also in the AP test that you don't even have a chance to do this on a calculator because you don't get a calculator. So they're looking to see if you can use what information is given to you to solve it. Okay, so then the last parts are percent composition and empirical formula. So last year you would have just had to figure out what's the percent composition of ammonia, NH3, or H2O. Well, this one is which one has more hydrogen. So percent composition is actually any percent question is always part divided by total, whatever you're interested in. In this case, it looks like we're interested in hydrogen. So I'll do ammonia first. So ammonia is made up of 1 nitrogen and 3 hydrogens. So if I go on the periodic table and find all those masses, that equals 17. 14 for nitrogen and 1 each for hydrogen. Now again, I am doing whole numbers because the question just wants me to figure out which one is higher percentage. Doesn't actually want specific answers. But it would have a couple decimal places there if I used all the decimal places. And then hydrogen weighs 1 gram each, but there's 3 of them. So that would give me the percent composition of hydrogen that's in ammonia. If I wanted to do water, same exact thing. I got to put my total on the bottom. So 2 hydrogens, 1 oxygen, collectively that equals 18 grams. And then on the top, I have 2 hydrogens and multiply by 100. Now, some of you might be able to do this in your head. Some of you might need a calculator, but let's check it out with a calculator. So when I did the ammonia, 3 divided by 17 times 100, I get in the ballpark of 17.6%. When I do 2 divided by 18 times 100, I get in the ballpark of 11.1%. So I think now you can figure out that there's a higher percentage of hydrogen in ammonia. And that's the kind of question you would get in AP. Okay. Let me move that there. Okay. Next one. The substance has an empirical formula of CH2 and a molar mass of 42 grams per mole. What's the molecular formula? So empirical formula is the lowest whole number ratio. But the molecular formula could be, it could be CH2 or any ratio of 1 to 2, 1 carbon to 2 hydrogens. So it could be, I'm not going to write too many on here, but it could be that. It could be that. Any ratio of a 1 to 2 ratio. So how do you figure out which one it is? You take the empirical mass, 1 carbon, 2 hydrogens, that equals 12 plus 2, 14. Actually, I don't want to do that. So that equals 14. And then I have the 42. 42 divided by 14, I think, is going to be 3. So what does that mean? I need to multiply that by 3. And I need to multiply that by 3. Whoops. And I think then that gives me C3H6. Okay. I think we got one more left maybe. Yeah. I think these are the most labor-intensive questions. They're not harder, but there's a little more work involved. So we have to figure out the empirical formulas. Answers are already below. So I'm going to probably just do one of these, and then I'll let you do the other. I'm just going to move this up just a little bit here. So I'll do the more complicated one, the one with carbon, hydrogen, and oxygen. So those are all percents. But if you had 100 grams of the chemical in your hand or on the desk or in a weighing boat, wherever you had it, 40.92 grams would be carbon, and then so forth and so forth. So you can immediately change all of these to grams. And what we like to do with grams is convert them to moles. So 1 mole of carbon equals 12 grams of carbon. Now again, there's on the periodic table, there is decimal places, but it's not going to matter with this question either. I think you'll see that a lot of times if you can't take shortcuts, I will take shortcuts because you'd like to be able to go faster if you can. Okay, so that gives you 3.41 moles of carbon. I'm going to do the same thing with hydrogen. So that percentage I can just turn right into grams. And then the periodic table, 1 mole of hydrogen is about 1 gram of hydrogen. So that one's going to be pretty easy to do. And then I have one more to do, the oxygen. I'm kind of running out of room here in the bottom, but we'll fit it in here. Whoops. Maybe I'll have to put it over here. On the periodic table, 1 mole of oxygen weighs about 16 grams. 54.5 divided by 16 is 3.4. Rounded, it rounds to about 3.41 moles of oxygen. Okay, so I cannot use decimal places. You can't have decimal places worth of atoms. So you can't have 3.41 moles, or I'm sorry, you can have 3.41 moles, but you can't have 3.41 atoms of carbon and then so forth of hydrogen and so forth of oxygen. You can't just get rid of those decimal places either. But what you can do is divide them all by the smallest of the 3 numbers, which is a tie. So I can divide them all by 3.41. That's not very good. 3.41 there. So that equals 1 carbon, 1 oxygen, and that's not going to be a whole number. That equals 1.3 hydrogens. So this is going to get a little messy here. I'm running out of room, but I can't just round that 1.3 to 1. But what I could do is I could multiply all those numbers by 3. Why would I do that? 3 times 1 is 3. 3 times 1.3 is really, really, really close to 4. And then 3 times 1 is 3. So what you have to do is you have to look at that decimal place and think about what number could I multiply that by to get that to be a whole number. So you're going to have things like this. You might have maybe sometime you do a question and you end up having 1.25. What could you multiply that by? You could multiply that by 4, and that would get you a whole number. The one we had was 1.3, and you could multiply that one by 3, whoops, to get the whole number. If you had 1.5, you could multiply that one by 2, and that would get you the whole number. So that's the idea. Okay, we didn't have any of those ones today. Well, I guess we did have one of those. So that is our ratio, a 3 to 4 to 3, a 3 to 4 to 3 ratio. The one up here, you do it this exact same way I did it. You take those percents, turn them into grams, convert into moles, and then divide them all by the lowest moles that you have. And that should get you to whole numbers. If it doesn't, you might have to do that multiplying game that we did with this question. Okay, and I think that might be it. It is. Okay, so that gets you definitely your review that you need to get started for AP Chemistry.